Okay, good morning. Hello. Can you hear me better now? Excellent. Okay, so thank you for coming back. So we started to talk about the space theorem last time. And as I said, the space theorem is both very useful, but it's also very useless. It's useful from the sense that it tells you a way to flip the order of A given B and B given A. And we are going to see some examples today that's going to help you solve a lot of problems. It's useless in the sense that you can just pretty much state the definition of conditional probability and then you can get the space theorem. There is also another theorem, it's called the total probability law. And that is a decomposition of an event into smaller pieces, and then you can add things up. That will also become very useful as we work on some practical problems. So to start with, let me remind you what these two theorems state. So this is lecture 2.6, and this is a problem that we're going to go over today. And let's skip them for now, and let's go to the definition. The Bayes theorem states that if I have two events A and B, and if I'm looking at the probability of A given B, I can flip it over by writing it as this function of B given A. Now, to prove this result, you just need to write down the definition of the conditional probability on the left-hand side. On the right-hand side, you can see that they're the same. So this ordering change can help you answer questions of A given B and B given A. You can flip the order, and that's the power of this Bayes theorem. The law of total probability is sort of a variation of the Bayes theorem. On top of the Bayes theorem, it also tells you a way to decompose an event B into smaller sub-events. And in this example, I'm partitioning the sample space into 3 sets. Now, in case you forget what this partition means, a partition means a collection of subsets, and then when you form the union, they will give you the sample space, and they do not overlap. That's the meaning of a partition. Once I can partition this sample space into smaller subsets, in this case A1, 2, and 3, they do not overlap. And if I want to calculate the probability, which is the size of this event B inside the sample space, I can just look into each individual smaller pieces. Each individual smaller pieces, they are the intersection of B and the A ends. Okay? So each intersection is A1 intercept B, A2 intercept B, A3 intercept B. So they're the intersections. And by the Bayes theorem, not even Bayes theorem, by using the conditional probability definition, I can write this intersection as B given A1 times A1, B given A2 times A2, and B given A3 times A3. Then I can write them all down. So this is the law of total probability. And let us start by looking at a very simple example, which we started to look at it last time. It is a tennis tournament where you have 3 types of players. Player A, player B, and player C. And in this game, half of the players, they are player A. So you can draw the set, and half of them, they are A players. Okay, half of them, they're A players. Quarter of them, they're B players. And then the rest, they are C players. A, B, and C. Okay. And then your chance of winning the A player is 0.3. Basically, it means that the A players, they're really, really good. And so your chance of winning them is low, 0.3. Your probability of winning over the player B would be 0.4, and then 0.5 for player C. Okay, so you have 3 probabilities of winning them. What is the probability that you will actually win the game? Okay, what is the probability that you will actually win the game? Now, as you tackle this problem, you should think about the following situation. As you enter the game, you do not know which player that you're going to play with. There is a random probability that you're going to play with player A. There is a random probability that you're going to play with player B, and so on. And if you play with player A, your chance of winning is only 0.3. Okay? So I'm asking, as you're walking into the game, you don't know who you're going to play with. What is the probability that you are going to win eventually? How do we tackle this problem? Using all these information available. Okay, so the suggestion is that can we use the law of total probability by partitioning the sample space into smaller subsets? Okay, and then let's look at this event B called the winning and see how we can decompose into smaller pieces and calculate them. So let's do that. So how about we define three conditional probabilities? Okay, three conditional probabilities. Let's call a win. Given that you play with A, probability of win given that you play with B, and probability of win given that you played with C. There are three conditional probabilities. And these conditional probabilities, they're already given to you according to the problem. What are they? Yes? Okay, so this is 0.3, this is 0.4, this is 0.5. Okay, so they're given to you already. According to this problem statement, you know them. Now, they're the conditional probabilities because if you play with A, then your chance of winning is 0.3, right? So there is a condition happening, and then you ask what is the probability of winning. So now, what is this half, quarter, and quarter? What are they? What are these numbers? Any thought? So what are they? Yes. Okay. So in words, they are the probability of getting A, the probability of getting B, and probability of getting C. Okay, so probability of A is 0.5, probability of B is 0.25, probability of C is 0.25. Okay, and these are the probability that if you walk into a game, before you even play with them, I just pick your opponent. Okay, their chance is 0.5, 0.25, and 0.25. And they're given by these probabilities. So once you have these formulas, then life is good. Why? You just plug into this law of total probability, and then you can calculate that. So let me just write it down. So here's the thing. You have probability of winning. The probability of winning can be written as the probability of winning given that you play with A times the probability that you play with A. Then you have the probability of winning given that you have B, and then plus the probability that you play with C. You just have all these 6 numbers. You multiply them together, so you have 0.3 times 0.5 plus 0.4 times 0.25 plus 0.5 times 0.25. This is the probability. And then you're going to get some number that, of course, I cannot calculate without a calculator. But you know what I mean, right? So you can plug into these numbers, and then you can get a number. And that is the probability of winning. OK, so let me flip the question around. Suppose you have won the game. Okay, suppose you have already won the game. What is the probability that you actually played with player A? Now that question is a little bit different from the conditional probability that I asked you, I told you, right? If you play with A, what is the chance of winning? That's 0.3. Now I'm asking, you have already won the game. That's the condition. You've already won the game. What is the probability that you played with player A? The order is flipped. Okay? The order is flipped. And physically, they mean two different things. One is that before you enter the game, suppose your opponent will be A, what is the chance of winning? That's 0.3. Now that you have already won the game, right? Event has passed, what would have happened in the beginning? So that is the other way around. Any thought? Okay. Okay. So basically, we're going to do some calculation and then find the probability. We're going to flip the order of the conditional probability. Okay. 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 So let's try that. Let's use the Bayes theorem. We want to look at the probability of play with A, given that you have already won the game. Now, do not get confused. This is not the same as probability of winning given A. The order has been flipped. Okay, the order has been flipped. And this is the probability of A given, probability of win given A times the probability of A divided by the probability of win. Okay, and this result is called the Bayes theorem. This is Bayes theorem. Okay, the Bayes theorem gave us a tool to flip this conditioning. You see the power of that? Because without this Bayes theorem, I sort of cannot answer this question of if I have won the game, who would have I played with? Right? So this is a posterior probability. I cannot answer that without the Bayes theorem. Now with the Bayes theorem, then life is easy because this is just 0.3, and then this is 0.5, and then the probability of winning is just this little box here. Okay, I have calculated in the previous step. And then you do this calculation, you will have another little box. So you can fill up the missing box here. So you see the usage of this law of total probability and also the Bayes theorem is used in this way of calculating some events, given smaller subset of events, how do you decompose them and how do you flip the order? It's that usage. And you can imagine that in many, many situations, these will come up. I tell you the forward process, I ask you the backward procedure. Okay, so that's the usage of the Bayes theorem. Is this question so far so good? Everyone's following me? Any questions? Yes.
Do we have to use this formula we came with and replace P of W with 1 and then solve for P of A? That gives us a
Where do you get 1?
So if we've won, then the probability of winning should be 1.
If you have won the game, okay, the chance that you actually played with player A is this number. It's not 1. It's not 1. Okay, and here's the logic. Your chance of actually winning the player A without knowing anything, your chance of winning depends on what kind of player that you have. The chance of winning depends on what player you have. And then the percentage of player is determined by this pie chart. Okay? So the probability of win is not 1. Okay? The probability of A given win is also not 1. Because if you have won, there are multiple causes that can lead you to this win. It could be that you played with player C. The chance of getting player C is lower, although your chance of winning over player C is higher. That can also give you this winning, right? So given that you have won the game, the chance that you have played with player A, you still need to calculate. That's not 1. That's not the number 1. Does that make sense to you? Okay. Other questions? Okay, good. Now, I have another example here, but I want to show you something even more practical. So here is another very interesting example. This is taken from this book, this example. Okay. So there are 60 students. There are 60 students in a medical school. HMS, of course, the author changed the name so that it doesn't overlap with another famous HMS. And assume that there exists a test to detect a disease. Let's say that's disease D. The probability of getting that disease is 0.001. So 1 out of 1,000 people, you will get that disease. You have a test. The test has a false positive rate of 0.005 and a correct detection rate of 1. Now, what is false positive rate? Can anyone give me an idea what is false positive rate? Yes.
When someone tests for a disease and the test results return rate is positive when it's actually not positive.
Okay, do you guys hear that? You actually do not have COVID, but then your test bar says that you have COVID. You get that? Okay? You do not have the disease. You actually do not have the disease, but then the test says that you have the disease. That's called a false positive. That's a technical term used in most of these medical sectors. Okay? Do you guys follow? False positive means that you do not have the disease, but then the test predicts that you have the disease. That's a false prediction. Correct detection means that you have a disease, and then the test says that you indeed have the disease. Good? Following that? Okay. Now there are type 1, type 2 errors, so let's forget that. I can never follow what the meaning of type 1 versus type 2. But just remember the definition, okay, of correct detection and then false positive. Now, this test is extremely good. It always detects a disease. Okay, this is an extremely powerful test. 1, okay, detection rate is 1. False positive rate is 0.005. Now, if you ever have experience doing machine learning, having a detection rate of 1 is not such a difficult thing. Can anyone give me a reason why? I can create a detector of always having detection rate of 1. How can I do that? Yes? I don't even need to overfit to the training data. Yes? You got it, okay? You don't even need to do any tests. Whatever you have, positive, 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 okay? So you always get this detection rate of 1. So having detection rate of 1 doesn't mean that your classifier is useful. So if someone tells you that, hey, I have this great invention of detection, always give you 1, it's 100% accuracy, okay? You ask, what is the false positive rate? 50%. That means it's just doing a blind guess. It's nothing better than a blind guess because it just always tells you 1, okay? And it's flipping a coin, okay? So having a detection rate of 1 and then false positive rate of 0.005. Okay, so now given that your test, you test positive for disease D. Given that you test positive for disease D, what is the probability that you actually have it? What is the probability that you actually have it? Many of these famous HMS experts answer that this is 0.95. Okay, all right. So something is wrong. Something is wrong. If you got positive from the test, what is the probability that you indeed have a disease? How do we tackle this problem? That's very realistic. Okay, that's very realistic. You never trust the COVID test results. You always ask what is the false positive rate and what is the true detection rate, and then you can calculate. How do you tackle this problem? How to tackle this problem? Okay, so what do we have so far? What do we have so far? Yes? So let's do some kind of ratio. But we're not, let's don't go to there so quickly. Let's write down some key quantities that we are familiar with, right? So we know, let's map our answers to the previous question. You have probability of player A, and then the conditional probability of winning given A, and stuff like that, so that we can use a language that we're familiar with and then tackle this problem. Let's do that, okay? So what do we know so far? We have three numbers, right? We have three numbers. We have three numbers. This is 0.0, we have three numbers, 0.001. So that's the first number. And then another number is 0.005, the second number. The third number is 1. So we have three numbers. What are they in our mathematical language? What are they? So let's define some symbols. D means that you have a, let's do this. There are two things, right? Let's call it actual, and then let's call it predict. Actual and predict. That's very easy to see, okay? What is this 0.001? Yes? Okay, so this is 0.001 is that the probability your actual is true. That's 0.001. Without doing the test, your chance of getting the disease is 0.001. That's given by this problem statement. Without doing a test, okay? Regardless of the test, you have 0.001. Okay. So how about this 0.005? Yes?
Let's say it's the probability that I test positive given that I don't have the disease.
Excellent. Okay, so it will be that you do not have the disease, so this is false, and then you predict that this is true. That's called false positive. You do not have the disease, and then the test tells you that you have the disease. And this is 0.005. Everyone agree with me? Is it okay? Okay. How about that 1? What is that 1? The 1 is true positive. You have the disease, and then the test tells you that you have the disease. So this is actual equals to true, and then the predict equals to true. Easy enough. Okay, so this is 1. So what am I asking? I am asking, suppose that you get a prediction being true, what is the probability that you indeed have the disease? See, I'm not asking these two probabilities. I'm flipping the things around. I'm flipping the things around. Now, when you get to this stage, problem is solved. Why? Well, you have all the formulas ready. Okay, so let's just, for the sake of completeness, let's just complete that. So what can we do here? The probability of actual given predict is that the probability of predict given that the actual, okay, so I'm flipping the order around, and what is the theorem? It's called the Bayes theorem. And so you have probability of actual equals to true divided by the probability of predict equals to true. So do I have these numbers? Of course I have these numbers. This probability is 1 because the actual is true, the prediction is true, that's just the true positive rate, so that's 1. This is the probability of getting a disease. This is 0.001. I know that. How about the denominator? I don't know that. But don't worry, according to the previous example, the probability of winning the game, you can always decompose it, right, into smaller events, and you can sum them up. That's the law of total probability, and we can apply the same trick over there to calculate this. So what is this? This probability of prediction is true. So this is the probability that prediction equals to true, given that your actual is true times probability of actual is true, plus the probability of prediction is true given that the actual is false, times the probability that the actual is false. Okay, so what is this? This one, this little thing here, is just the sum of these two smaller subsets of events. This is the law of total probability, nothing crazy. Okay, I'm decomposing this event into two smaller cases. This is the first case where your actual is true. This is the case where your actual is false. Two cases. Now, given this formula, I know that this is 1 because this is the true positive rate. This is 0.01. This is the probability of getting disease. This is what? That you actually do not have disease, and then it declares that you have disease as a false positive, so you have 0.005. It comes up here. Okay, so this is 0.005. Now, the last one is this probability of your actual is false. How do we get that number? Just 1 minus. This is 0.999. Okay, because the chance of getting disease is 0.001. So 1 minus that would be the disease, the probability that you do not have the disease. So you have all the numbers ready. You see here. You have the numerator, you have the denominator, everything is ready, so you can just plug in the numbers. So you have 1 times 0.001 divided by 1 times 0.001 plus 0.005 times 0.0999. And that will give you a number. And this is the probability that if you receive a test, the test says that you have a positive case, what is the actual probability that you have a positive case? And you can imagine that with this false positive rate being a high number, then your chance of actually getting the disease will be actually low, right? So regardless if you look at your testing kit, positive, but then if the false positive rate is high, you do not need to worry about that. Okay, so that's another very, very practical example that you will run into in a daily basis. People say that, okay, I have this kind of test. You can ask false positive, false negative rate. Tell me all these numbers. You can actually do the calculation. Right away, you can tell whether the number is valid or not. So this course, I think, as you are going into this stage of the course, you see that this probability thing is not just gambling. I hope that I clarify this notion for you. Right? It's not just about gambling, playing the poker. It's not about that. It's really, really practical. You run into these problems in a daily basis. Just an example here. Okay? Good. Any questions before I move on? Yes, please. Can we find this problem somewhere? Yeah, it's in this book. Okay, so when you become professor, you have a stack of books. So you just randomly pick one, and many of these problems are very interesting. Many of these problems are interesting. You can go to libraries. You can check out many textbooks. So every textbook they have very interesting problems. You sit down and work on those, and you will get the flavor. Okay, you work on a few problems, you can solve all the problems. So if you're looking for additional exercises, these will be excellent places that you can get references. There are a couple more popular, we call popular textbooks. If you're interested, you can send me an email. I can just send you a list of those textbooks, at least those books on my bookshelf. Okay, so if you want those, let me know. But I think I would not recommend you to work on all these problems. I would just say, spend some time understanding the basic principles. And all these problems, once you understand the basic principles, they're more or less the same thing. Does it make things clear? Okay? Okay, good. So let's move on. Can I? Okay. So let's move on. Probability can be applied to problems beyond the health sector. We can also use it for communication theories. Okay, so I know some of you here, you are in electrical engineering because you want to study, hopefully no longer 3G, 4G. Nowadays we're talking 5G and 6G. But in many cases, there are some basic principles behind this communication. The communication systems that we use today, they're digital. And by digital, I mean that you do not send the analog voltage over the wireless channel. You encode your signal into binary bits, and then you have a carrier to send these binary bits out through the wave. So here is a very practical problem. It's a simplified practical problem. It's a two-channel communication. And the problem goes as follows. You have this communication channel, and then the probability of sending a 1 is p, and then the probability of sending a 0 is 1 minus p. Given that a 1 is sent, the probability of receiving 1 is 1 minus eta. Given that a 0 is sent, the probability of receiving a 0 is 1 minus epsilon. Okay, and this diagram is given as follows. You have 0 and 1 at your transmitter side. Then you want to communicate this 1 to the receiver. These two numbers, epsilon and eta, they're very small. Okay, otherwise you have a really bad communication channel. So these numbers are small. If you send a 1, there's a good chance that you'll get a 1. You send a 0, there's a good chance to get a 0. There's a probability of getting a 1. There's a probability of getting a 0. Depends on your message. And so we ask, what is the probability of getting a 1? What is the probability of sending a 1? What is the probability of getting a 1 given that you send a 1? And what is the probability of sending a 1 given that you receive a 1? You can ask all kinds of questions like that. Okay? So I'm not going to go through all the details of this problem. I will ask you to work on some of those. In fact, it's part of your homework exercises. Okay? If not the homework 1, it should be, if not homework 2, it should be homework 3. It's there. Let me just give you some quick hints as you are working on these problems. Let's look at the second one. What is the probability that you actually send a 1? That is very clear from the diagram. You don't even need to look at that side. Just look at the left-hand side. What is the probability that you send a 1? P. Okay. The transmitter doesn't need to communicate with the receiver. The transmitter just sends something out. And that's P. What is the probability that you receive a 1? You receive a 1, there are two ways you can get a 1. One is that you actually send a 1 with a correct transmission. So you get this. And then the other one is that you send a 0, but then you mistakenly, and you get a 1. So that's the second path. So there are two cases to give you this. So you have probability of receive 1, given that you actually send a 1, times the probability that you send a 1, plus the probability that you receive 1, given that you send a 0, times the probability that you send a 0. Okay, so you can do this calculation by yourself. And then you ask, hey, what is this conditional probability? Look at the diagram, that if you send a 1, you receive a 1, you get a 1 minus eta. You send a 0, you get a 1, you get epsilon, right? S equals to 1 is P, S equals to 0 is 1 minus P. So all the numbers are ready. The probability of receive 1, given that send 1, this is just 1 minus eta. It's given by this diagram. The last one is interesting. You send a 1, given that you receive a 1. And so this is the probability that you receive a 1, given that you send a 1, times the probability of send 1, divided by the probability that you actually receive 1. That's the Bayes theorem. So you can plug in and then find the results. Okay, so this exercise, as I said, I'm not going to go through in great details because this is part of your homework assignment. And I hope that this assignment will give you some practice of applying the Bayes theorem, law of total probability, looking at this conditional probability, posterior probability, flipping things around, dividing things. So that is the purpose of this exercise. So I hope you will enjoy this problem. As you see this problem, if not this homework, it will be the next homework. You will see that. Is it okay? Okay, good. So now for the remaining time, let's go back to our big problem. The very interesting 3 prisoners problem that I owe you. Okay, I still like this drawing very much. Okay. So let's recall the story. There are 3 prisoners, and the king, not me, decided to pardon 2 prisoners, and then have something fun with the 3rd prisoner. Okay, then you are prisoner A, so you're sort of neutral, and then there's 2 other prisoners that are unhappy. Then you have a guard you can talk to. The guard cannot talk about your case, but then the guard can talk about the cases for B and C. So without doing anything, your chance of being released is 2/3, because out of the 3 people, 2 will be released. So your chance of being released is 2/3. As you talk to the guard has to tell you B or C. And no matter which one the guard tells you, your chance of being released would reduce to 1/2, because it would be either you or B or you or C. Okay, your chance of being released would drop. That just doesn't make sense. Something has gone wrong in this logical argument. And what has gone wrong? Yes, please. Okay, so we're getting a very, very key point. There's some kind of independence going on. There's some kind of independence going on that will make this argument of this prisoner A flawed. Okay? So independence, keep in mind. But before we go to this independence, let's do some calculation, again using all the tools that we have learned so far. And my practice is always to use the symbols that we are familiar with. Okay, conditional probability, Bayes theorem, law of total probabilities. These are the tools that we have. And I promise we can solve this problem with all these tools. So let us define the following probabilities. Actually, I have this typed here. Okay, so define the event XA be sentence A, XB sentence B, XC sentence C. Okay, so these are the three events. GB means that the guard says the B is released. And without laws of generality, let me just assume that the guard says B. It could be C. Okay, it doesn't matter. So let's calculate the probability of XA, XB, and XC. Let's calculate these three numbers. What are they? Mm-hmm. 1/3 each. Perfect. XA is 1/3. XB is 1/3. XC is 1/3. It has nothing to do with the guard. That's just the pure probability of being released. 1/3 each. Okay, so that is good. Now, when the guard comes to the game, what kind of probability do you want to calculate? Can anyone give me a suggestion? Clearly, this is not XA anymore. Some kind of conditioning. What condition on what? Yes. PXA, so you want to calculate XA given GB. What is the physical meaning of that? What is the physical meaning of that? Yes? Okay. This is the probability that A is sentenced given that B, the guard says B. Do we have access to this number without doing additional calculation by just looking at the problem? Not quite. Not quite. What do we have instead? What do we have instead? This one, not quite. We don't have access to this number. Yes?
We have the probability that the guard says B is released given that A is sentenced.
Okay. Probability of GB given the XA. Do we have access to this number without further calculation? By just looking at the problem, do we have access to this? Do we have? Okay, someone says yes. How about other people? Do we have access to this number? Think about it, okay? You are A, okay? XA is to sentence A. The guard knows, okay? The guard knows. And then if sentence A, what is the probability that the guard will say that B is released? Do we know that probability? Yes.
It should be 1/2, right?
Why is it 1/2?
So the guard says that it is B. So B gets out of the equation, and we're left with A and C. So we should the total number of possibilities becomes 2, so it should be 1/2.
But the guard cannot talk about you.
You already said that B is the one that's going to be.
Yeah, right? So you just gave us two pieces of information, okay? The guard cannot talk about you. The guard says B is going to be released. Then what else can the guard tell you? Okay, so let's think about that again, right? So probability that, so let's say the, you have a comment here?
I was just going to say that the probability that B is released given that A has been sentenced is just 1.
Why is it 1?
Because only one prisoner is going to be sentenced. So if A is already sentenced, then both B and C have to be released.
Okay, so let's calculate that, right? So now there are three equivalent events, right? So GB, let me see, XB, GB, and XC. So there are three cases, clearly, right? So let's work on the easier one. Okay, this one. Okay, the second one. Let's say the actual execution is B. Okay, actual execution is B. So B is sentenced. The guard comes to you. And then can the guard says the B will be released? Impossible. He knows that the B is sentenced. So that's 0. It just will not happen. Okay? Okay, let's look at this case. The guard knows that you will be sentenced. All right? He knows that you will be sentenced. And then what can he say? How many choices does he have? 2 choices, B and C. And then the guard can tell you either B or C. So he has a choice. 2 choose 1. That's 1/2. So you're right. Okay? How about C? So if the guard knows that C is sentenced, okay, so C is gone, he comes to you, and then he cannot talk about you, then the chance of saying B has to be 1. See the logic? Okay, so these 3 numbers are given. These 3 numbers are given. And then what you are interested in is this. This is the ultimate question that you're asking. And do we know the answer? Yes, we know the answer. We know the answer by using what tool? Bayes' theorem. The Bayes' theorem says that probability, the A, GB, is just that the probability of GB given A times the probability of XA divided by the probability of GB. So this number is 1/2. This number is 1/3. Okay. How about this GB? This GB is, now I'm going to do a little bit faster. It will just be 1/2 times 1/3 plus 0 times 1/3 plus 1 times 1/3. So that's just the decomposition. I guess many of you are already familiar with this law of total probability. Just decompose these events into this times that, this times that, this times that. Right? So it will be just the sum. So we can do the calculation. This is 1/6 divided by 1/6 plus 0 plus 1/3. So what do I have here? 1/6, help me with this number. So this is 1/6 plus 2/6. So you have 1/6 divided by what? 3/6, so you get 1/3. You do everything to the end of the day, you show that this is 1/3. Okay, and here's the independence. Who said independence? Okay, so this independence come into the game. Right at this moment, look at this probability and their probability. They are the same. Why? The ratio, remember the conditional probability? Okay, the ratio is the ratio between the intersection over the smaller subset. Okay, and here is the probability of the original event over sample space. The ratio, they match. These 2 are equal. It means that the presence or absence of this GB doesn't matter. They're independent events. Okay? And so regardless of what the guard says, your chance of being released is always 1/3. There is no logical issue here. Okay? Okay? It's just that the way that you look at this problem is a little bit flawed. Okay? So I hope this exercise gives you another way of looking at these problems, looking at these tools. Very interesting tools, okay, very useful tools, very practical tools, solve a bunch of problems. I hope you guys can enjoy it and then find it useful in your problems as well. Okay, so that concludes this lecture and also chapter 2. And when we come back next time, we will talk about chapter 3. Please download the slides and prepare for that. Thank you.